All right, so there's definitely a few things I need to talk about for us to have enough information to do the project in whole. But what I prefer to do is have you drive me with your questions, and I'll make sure we get there. Do you have any questions? Yeah.
Could we talk about Mmap again?
Yes, absolutely. Let's talk about Mmap. All right. So the need for Mmap arises from our need to have multiple processes being able to look at the same and work with and manipulate the same memory. Right? In this case, in the context of this project, our map, a bit representation of that map, will be in a shared memory segment, and multiple processes are going to be moving player bits around and grabbing gold bits off there and so on and so forth. So shared memory is the mechanism for doing that, and let me see. Oh, what did we have here? That was 31 I want. Okay, what did we do last time? So this was our header file. We were just talking about the bits in that. This was a sample map. This is, what is this? Shared memory. We copy that, whatever that is. So the idea is that the first player playing the game is responsible for creating the shared memory that will be used by all the processes. The last player to leave the game is the one who should remove it. Okay. Now, we haven't really talked in detail about how we determine that and make sure that happens correctly. That's part of what we'll do today. But for the moment, we can, for the sake of this exercise here, assume that this person is the first to join the game, so they're going to create the shared memory this way. Note that it's very similar semantically to just a straight open call, a system open call, right? It returns a file descriptor. And just like when you open a file and create a file, that file is initially empty. So there is no memory currently allocated by virtue of doing this. So it's a two-part process where first you have to create that memory in the same sense that you create the file, and then you need to grow, if you will, as much memory as you need in order to represent that map. And the mechanism we use is the same mechanism we would use if we needed to grow a file to a certain size, and that function is ftrincate. So we would have previously, probably even before we do the shared memory, read in the map file and determine the amount of memory needed. That is rows times columns.
That's just a regular read.
Right. So it's fine to avoid system-level interactions when you're able to. And this is one case where you're able to. I would resort to just normal C++ fstream, right? Just use get line, read in line after line. You can look at the length of the string to find out the number of columns, the number of times that you iterate through the loop reading in lines is going to tell you how many rows. And then keep in mind that that very first entry in the map file will be the number of gold, so there's one extra line in there.
I have a quick question about that, actually.
Yeah, go ahead.
Is the name of the file going to be hard-coded, or is that taken in at the command line? Or something
I
else?
would, yeah, you know, I need to, yes, so on my to-do list, which I'll never get to, I need to be a little bit more specific on my desire there. I would desire you to take it from the command line. So argv sub 1. Yes?
Where is the code that determines where the gold line should be written?
So the process will be, oh, let me see. Let me start a notes about gameplay, or what do I want to call this? Code design notes. I think what I want to do is come on. There we go. Nope. Oh, did I just write that? No. All right. I want to call this code design notes. I'm going to give it a CPP extension for the sake of getting nice syntax coloring if I throw bits of code in there. So first, determine if first player, if yes, create shared memory with SHM open, read in map to determine rows and number of columns. Grow shared memory using truncate. So let's see, what were we doing with this code? There's the open. Remember, error check every single function system call. There I'm opening, so I wouldn't do it in this order. But all right, so let me actually go ahead and move it. Let me say 23 through 28 delete. I come up here. There we go. So that becomes that comment.
Does it actually matter the order, as long as you leave it?
No, well, no. So I mean, I could open up the shared memory, and then I could read in the file, and then I could have truncated after. Here's the thing, though, is you want to, if anything goes amiss, you want to clean up. Okay. So if I've done this already, and let's say that in this case I've hard coded it instead of reading it from the command line. If my file.txt doesn't exist, then I need to abort mission. So if I've opened this first and created this shared memory, and then the map file doesn't exist, I need to close it and unlink it, right, to clean up. And so I'm going to minimize my hassle with cleanup if first I try to open the file, and if it doesn't exist, I bail out, and then I've never opened this and don't have to clean it up. Yes?
What does unlink do?
Unlink is the system nomenclature for remove. If you unlink a file, you're removing a file.
Where does that term come from? Unlinked. Unlinked. Named it for a reason.
Yeah, it's after Zelda, Link, and no.
I know there's something.
They're entries in the file system table. So this is showing each of these files has one link. I can link shared memory.cpp. I'll call it FDSA. Oh, I can't. That's because I've got this mounted on my Mac. So let me go up to. This is in the virtual machine's own file system and not mounted. So let me try it again. Let's see, is there anything in here? With mask, without mask. Oh yeah, I created these, didn't I? Hang on, let me do this. Let me copy that up there. All right. So this is indicating that this has one link in the file system table. If I say link shared memory.cpp to FDSA, now I do an ls-l, now we can see that there are two links here.
So is FDSA like an alias or like something?
Exactly. These are two entries to the same physical file, meaning that shared mem.cpp has no more priority or no more importance than FDSA. If I remove shared memory.cpp, this is still that file. Right.
It's not a broken link.
Right. It isn't like shared memory.cpp is the master record and then FDSA is an alias. They're both pointers to the same physical file.
Is that the difference between a hard link and a soft link?
A symbolic link.
Yeah.
A symbolic link is more indirect. So the thing with this is, I'm being very specific when I say they're both entries in the file systems table, because you don't see it so much anymore, but each of these is a different file system, which means that now these are all special, so I have to do a little bit of hand waving. But actually, let's see if we can find if they've done it on Jaguar. Yes.
You know, if you delete the original file, the symbolic link becomes broken. But if you delete the original file,
Right. So that's what I'm getting to is the distinction between a link and a symbolic link. So let's see. This is on Jaguar. I'm trying to find. See right here, this is the root file system here. Oh, you know where I would have that? I think I might have it on my own computer. I'm trying to find a better example of file systems.
so what do you have here? Triple SSH or triple recursion? Like you went from your computer to Vagrant to Jaguar.
I logged into the virtual machine, then I logged into Jaguar, then I logged out of Jaguar, and now I logged in from the virtual machine to a machine I have at home that has an old, when my kids were a little younger, one of those cards, those flash cards for multiplication. I got that taped over the power key because the damn cat keeps walking on it. But that'll come later in the course, the more advanced stuff. Yeah, it looks like I've since reconfigured it. So here's the deal: is in the old days, the space on a hard drive was you felt more constricted. Now, I mean, right, they're vomiting out terabytes. But in the old days, it was more constricted, and so the kinds of issues you would have is if you had this kind of setup right here, this is just one mount point for my entire drive, and I don't know what the drive is. Let's say it's a terabyte. Then that means that everything, right, if I look at ls/, the bin, home, where all the home directories are, the lib, temp, all of these are part of the same file system. And I could, the way it is now, I could do that ln and link basically any file on that entire system, regardless of where it is in the hierarchy. The traditional way of dividing up a system is you actually create distinct, thank you, partitions on your hard drive, and each partition becomes its own file system. And you would, for example, have the home directories in their own partition. You would have temp in its own partition. You would have swap in its own partition. And the reason for putting these in their own partitions is that if they get filled up either accidentally or maliciously, a good accidental reason is people always use the temp directory for temporary files for their programs, and if something goes haywire and the thing just grows till it fills the entire file system, in the scenario with the way my computer is configured now, if that file system fills up, then the operating system stops behaving properly because it's always creating temporary files, right? And if there's no space on the hard drive for its temporary files, then high-level processes start bugging out. So by making this its own file system, if temp fills up, that's fine. The rest of the computer is safe. And likewise, if someone in their home directory fills something up, that's not going to affect the rest of the system either. So that's one of the main rationales for dividing those into separate file systems. The disadvantage is the traditional link command can't link across file systems because it's actually putting another entry in the file system table. Right, and those are different file systems. So that's where symbolic links come in. If I do, let me get out of here. Now I'm back here. If I do ln -s, and then what did I call that file? Whatever. Code.cpp. Then you see these are still just a single link. And this, and you can see that they actually have a flag here to specify that this is a symbolic link, right? Whereas before, with the traditional link, if I link to FDSA with a hard link, so this is 2 and this is 2, but that's because these are both referring to the same physical file, whereas this is just this. Now, note the size. So if I just say vim code.cpp, what it does is the symbolic link resolves, and I open up FDSA, right? That's FDSA. However, if you were to look at this, this is just a file that has, in this case, 8 bytes in it. And what are the 8 bytes? FDSA. So it's literally just a text entry, and then the file system is just doing an indirection there, and it's opening it up. It's saying, okay, wherever the current directory is in relation to this, I'm going to look for this file and open it up. So you can create symbolic links that don't link to anything. And here's this referring to this, right? And it's going to be resolved at the time I try to access it, and it's at that point that it says, which means that this file doesn't exist.
So is the symbolic link kind of like a pointer to a pointer, where a hard link is more of a pointer to an actual
Yeah. I think that's a good analogy.
So I see FEWK has 9 bytes.
Right, that's because if you count this, there are going to be 9 characters here.
So when you unlink, is it like you're not actually overwriting anything in the file system? You're just not pointing to that location memory anymore? So
That's right, and then there's a little bookkeeping so that it knows that those blocks on the drive are available for use again.
But there's still, all the bits are still in the exact same position.
Yeah. and so that's consistent with how primary memory works when we're writing our code, right? Once you, if you're with dynamic memory, you do new and delete. Delete is merely a releasing of the reservation of that memory. It doesn't take extra time to scrub it clean. Whatever was there is still there, which has been a vector for malicious code and viruses and stuff. When they find some sort of weakness and they're able to access some, like you store a password in main memory. That's actually how how it used to be done a long time ago. When I was in my youth, and I wanted software that I didn't pay for. I was young. What I would do is I would just scan. I'd basically just scan memory and see if I could find the validation password they wanted. It wasn't all tricky encryption now. It was just they just had some password that you entered to unlock the software, right? So you could scan memory and find it and enter it, and there you go. So, yes.
So I see that FDSA and hardcode.cpp, they have the same size, 1565.
Yes.
There's only one physical file in
Yes,
the
that's correct. Those are just
system. So
links to it.
two are just like pointers pointing to
Yeah,
that
yeah,
physical
yeah,
file
yeah,
system,
yeah.
and they are displaying the size of what like they're pointing to. So what we see on the terminal isn't the actual file, so to speak. But if we take up the sum
It's
of
just
those numbers, we would say, oh, we have two duplicates. So are there two duplicates? There's only one duplicate in there, right? If we look at the size of those two, they're both 1565. We would think that, oh, there's two of them now.
Well, let me see, what is it? So if you look here, here's hard. So this is looking at disk usage. And note that this is intelligent enough to know not to double count. At least I think it is. Here's hardcode.cpp, and I don't see FDSA in here anywhere.
What's 4 in what unit?
Huh?
4 is what unit of measurement?
Blocks. Probably 512 K blocks or something like that. All right. I don't know how the hell we got here. I mean, it's all good and I like it, but I think I've exhausted where I was going with that. So let me return to where I was. Oh, there was one other thing I wanted to ask. If how do you look at a long listing of a directory, right? So if I say ls-l vagrant, I see the contents of that directory. How do I look at the long listing of the directory itself?
LL.
LL?
Just LL.
What's an alias?
LL is just an alias.
It's D. That means don't go down into the directory, right? Why does it have 4? Which 2 and which 2?
The FDSA plus the hardcode.
So if you wanted to say 2 of them would be, well, it's this entry in the directory and this. Everyone understands what I did, right? I just went up to the parent of the home directory here. So this is one of them. That's correct. Ooh, that's cool. This is the other one. That's 2 of them. What are the other 2? Oh, good answer. Yes, that's exactly right. In that case, it'd be dot and dot dot. Yeah. All right. Vagrant 205. Okay. We open up the shared memory. We were dealing with the notes. Read in the map, create the shared memory, grow it, I think with ftruncate. Ftruncate wants a file descriptor, so that's the shared memory file descriptor. You give it the rows and columns, do your error checking. Now, at this point, what we need to do then is one of two things. Either you reread this, you have to convert this, right? You have to convert this to bits that are mapped to the shared memory. And you can either read it in again, or what I did in my implementation is I just read in the file into a vector, I think. And then I just rifled through that vector when I wanted to go through it a second time. So you go through it a second time, and you need to take, I don't think I didn't save that. So you have that number, you store it somewhere. Note that there are only two types of characters, either spaces or asterisks. And when you do ftruncate, let's look at the man page for that. All right, here's the line I'm looking for. If the file previously was smaller than the size that you specify in truncate, which is our case because it starts out empty, it shall increase the size of the file. If the file size is increased, the extended area shall appear as if it were 0 filled. Okay, so that will basically, our shared memory will be filled with zeros. All right, what is a space and what bits are flipped for open space?
Not all zeros, there are some bits. The asterisk station. Don't know what that is.
Well, if you're one of the players, it's those bits. If it's a wall, it's this. If it's gold, it's that. If it's fool's gold, it's that. And now I've exhausted my bits. So the answer is it's all zeros if there's nothing there. Okay.
Oh, that's right. We're not using that.
So there's really only one thing you have to look for. If it's an asterisk, set the wall bit. Otherwise, don't do anything. That's it. Right? I get people who create these big, they take that test program, right? If you look at that test program that came with the tarball, there's either a switch or a set of ifs in there. If it's player 1, you flip the player 1 bit. If it's player 2, you flip right, you flip this bit, you flip the gold bit, the fool bit. There's nothing in the map but asterisks or spaces. So don't put this big switch because none of those, you're not going to hit any of those branches because none of that's in there. Remember, that was just a simple test file to kind of show how that map class works. It wasn't intended to be a model on how you structure your code. So yes.
But if we do hit a new line when we're reading in that file, we have to keep that in track because we will have to increment our rows position.
Oh yeah, sure, yeah, of course. Yeah, that was the original reason for reading in the file, was to determine the number of rows and columns.
I mean that in addition to the asterisks, we also need to be able to detect where exactly a new line occurs.
There's no new line. If I've got, right, this is, that's byte 0. This is byte 17. This is byte 18.
What about those? You know how you can make the $sign characters appear? Aren't those new line characters?
They're not in your memory. Your memory, this is your memory. There you go. That's what your memory should look like, except instead of asterisks, you have that G wall bit flipped, and where you have spaces or zeros.
We just know based off of those number column variables, right?
That's right, because you read in the file originally and you got the number of rows and columns. So if I have that big long length of memory, I guess I ought to put this in notes. How do I want to say this? The bit representation of the map is a one-dimensional array. I mean, we just call it an array, right?
That's inside the file itself.
Off the offset, so given user is at current column, or whatever, user, given location of interest is at current column, current row, offset equals,
Current row times.
no, and then given map with number of columns, number of rows,
Current column times number of rows. Current row times number of columns plus current column.
and to go the other direction, and the other direction.
Offset minus current column. In parentheses divided by the num column. Just as an algebra you would do. Solve for the variable. No.
Yeah, so tell me what it is.
Offset minus the current column. In parentheses, divide that whole expression by num column. Just algebra. And then for current column, it would be offset minus the current row times the number of columns. No. Offset minus the quantity current row times the number of columns.
That? Is that what you're telling me?
No, I mean
Offset minus current column divided by current row.
current column. Offset
That doesn't seem right.
Offset
So,
minus
right.
the current row times number of columns.
How about this? Let's see, how do I want to do this? Let me do that. got to take all of this, and I got to move it this direction, and do it again. So this is zero pipe. All right. So if my offset is 8, what's 8 divided by 5? 1. What's 8% 5? There you go, 1, 3. And going the other direction, which we had up here. So if we had 1, 3, 1 times 5 is 5 plus 3 is 8. You all buy that? Okay. So those are your conversions for that. So that's all one big long array. We can get back and forth this way. And then we grow the shared memory. We iterate through Mmap, initializing shared memory with g_wall. Now there's something that needs to happen here. At this point, after you grow shared memory using truncate, you can use the shared memory exactly the same way you use a file, and that is with the read and write system calls. That is painful to do. We would like to treat it the way we treat normal main memory, and that's where Mmap comes in. Okay, so Mmap will take a file, a pointer to shared memory, or not a pointer, a file descriptor. It'll take a file descriptor and end of sentence. So you can do this to a normal file if you wanted to. Doesn't have to be shared memory. I have this a little bit recipeed. The important thing is this right here, and that is the number of bytes that you're mapping. Yes?
I was trying to compile that line. The prod flag is
Oh, I'm sorry. This should have been prod read.
okay.
So I probably accidentally deleted it or something.
Can that region rows times columns be less than the size of the file itself?
Then it can be whatever you want, but it'll map less of the file then, if you make it less.
Make it more.
I'm not sure what will happen if you make it more. My guess is it would get a seg fault or something like that if you tried to access it. So once you've done this, so what you're doing is you're creating a pointer here, and now you access that shared memory through that pointer as if it was just normal main memory, right? Now it's a piece of cake. So you can do your map pointer so you spin through a loop, taking that file, converting the asterisks to bits.
That will modify the file itself.
And it modifies the shared memory, yeah. Which means that if another process starts up, that memory's already been initialized, And so all they have to do is drop their player on there. So that gets to where we have to go with this, is right here, use Mmap to enable use of shared memory through a pointer. Yes?
I'm guessing that getting pointer that could also work for files inside your physical file system also.
That's correct. Anything that you can attach a file descriptor to. All right. So we initialize it, then randomly drop fool's gold and real gold. And I even think we threw out some code. Yeah, that's what this is. You just generate a random number somewhere in that array. If it's already got something in there, like it's got a previously dropped fool's gold, or if it has a wall in there, you just do continue. It'll iterate through the loop again. And as long as this number is greater than 1, drop a fool's gold. If it's equal to 1, that's your final one to drop, and you drop the real gold. You come up with whatever algorithm you like. I thought this was just kind of an easy way of doing it. And then decrement gold. Let me see. It would, yeah, and that'll work, because if you've found something, you're continuing and you're skipping line 68. So that should work as written. That drops your gold. Next, you have to drop a player. And if there are no other players, then your G_PLR0, and you just do basically something nearly identical to this, except you're just dropping that player where there's an empty spot. Okay. So randomly drop fool's gold and real gold, randomly drop player bit, while loop.
What if it happens if you drop the player and they actually land on the real gold?
Then your loop would loop again because it isn't empty.
So like you're flying with the parachute and you land on the gold itself. Oh, I'm doing that instantly.
Any questions on that? Yeah.
It's not really on that, but it's more of a thing about.
Yeah.
So you didn't go over this, and I'm assuming for a reason, but like the error on when Mmap fails is it returns map failed, which is it legal for us? It's like it's not returning -1. It's kind of a silly question, I guess, but can we just?
You should definitely look for map failed.
I know, but like in the I don't know, I'm not talking well.
No, you're
In
fine.
the return value, it does not return -1. It returns a value of map failed. Which is it like like if we put in all caps map failed, is that gonna work as?
Yeah, that's actually, that symbol is actually defined. So
Okay.
you would literally use that. You would literally have, where's my mmap? So you'd say if map pointer equals,
Okay, yeah.
then you'd have your p error. Any other required cleanup, exit.
Well, first thing, map pointer is type of unsigned character pointer, so a -1 is a type of integer. And second, we don't actually know what the internal representation of that map failed is, so we can't say just equals to -1 because we don't know what it's.
Well, we don't say equals to -1 because that isn't how you determine whether mmap failed.
Yeah.
So yeah, and so that's the reason why when I'm up here I spend half my time in the man pages is because when you're doing systems programming, unless you got this, you're doing this every day and you got this stuff memorized, right? You're always hitting the man pages to find out usage, how you determine if there's an error, how you report an error, and so on and so forth.
Now, there are several specifically defined constants such as null that we know have some value, such as 0, but for others we don't actually know what they are, so we only resort to using the name itself.
We use the name itself because that's what the man page says. And it isn't -1 for a reason, and usually these end up being historical reasons, so we could delve into that and figure that out, but at this stage in the game we just want to follow the man page. Alright, so let me see, where does this get us? That gets us on quit. So this is if yes. Now we need to talk about if no. Yeah, let's talk about if no. We definitely have some if no stuff. The accepting keystrokes happens in either case. If you're not the first player, determine first free player bit. Remember, because I could have players 1, 2, and 3 stop, the second player drops out. Excuse me. The second player drops out, and then another player comes on board. They don't get the 4th bit. They get the first free one, which would be, in this case, 2. They would pick up that one. Yeah? Okay, so that's what this is talking about. Determine first free player bit, and then drop player on. Drop player on in random location. While loop to accept keystrokes. On cue, remove player bit. If last player, remove shared memory. Yes?
If determine if first player, if no, I think we should have to look inside the we have to look into the file system to actually find the shared memory and grab a pointer onto it. We need to find the location of the shared memory.
If no, open up existing shared memory, call Mmap. Now, you can always find the shared memory because you're the programmer and you know the name that you used, right? It begins with a slash and then it's whatever you called it. And keep in mind this is a single executable. So you've got it in a different part when you were creating the shared memory for the first player. Whatever you called it there is what you should be calling it here when you open it up.
Accessing it by the name.
Yeah. You have a consistent name. So then, where does that take us? Let me think. On movement, you got several things to consider. Consider with movement. Don't move if wall or another player. I think that's what I want, unless the PDF says otherwise. I don't think you want to march over another player. You could seamlessly because they're different bits, right? Then both bits are triggered. Whichever is the higher player is probably the one that will be rendered, and then one of them moves on. You can? All right. So you don't move if it's a wall. Don't allow movement off map if player does not have possess. Is that right?
SSUS.
Thank you.
Possess is
I'm sorry, is that?
SS.
Yeah, there are two S's. All right. If player does not possess real gold. And then, otherwise, what if they do move off the edge of the map and they have the real gold? You win, right? So there's some logic in there you got to figure. A lot of it is they hit K to move up. You got to do the calculation that we did with the percent and the divided by to figure out whichever way you're going, whichever direction you're going. You got to make sure that it isn't a wall. You have to make sure they aren't going off the edge of the map if they don't have the gold. If they do have the gold, you need to bail out of that while loop, print a U1 message, and then let the thing quit. So that you have to do that kind of logic in there. Yes?
So when it comes to like two players that are over each other, can you kind of explain a little bit more what you have by check to see like one's lower than the other?
Oh, you don't have to do anything. I was just musing out loud, and I think this came up momentarily last time, is that what happens with what you visually see. Now, what you visually see is all handled by that map class, so you're really not concerned with it. I'm speculating that if I was to look at my algorithm, it simply rifles through the bits and it says draw 1, draw 2, draw 3, and whatever the highest one is what's going to be visible to you. You don't have to do anything. Basically, you're going to have two bits in the same byte, and then when one of them moves off, that one bit gets turned off and gets turned on in the adjacent square. All right. So, we're not quite there yet. We have a couple more things to handle. First, let's talk about synchronizing the different processes. So, you don't want two processes writing to the shared resource at the same time. They could clobber over each other and create issues. So what you need to do is, this is where semaphores comes in. Semaphores is another inter-process communication idea, and the idea is that so semaphores semantically can have have some sort of integer value. They can have 10, and then the two calls are, oh hell, let me find the code. Let's just look at the code. All right, so first question. How do you determine whether you're the first player?
You create the shared memory, and you get flipped to O1.
Say that you create the shared memory in what?
Or if your bits flipped to X O1.
All right, I think you're on the right track with you create the shared memory, because if we look at
Oh, but you first have to look.
So this will open it and create it if it doesn't already exist. How can I determine whether it already exists? I want to do that. Let's say, let me put it this way. I want to do this line of code, but I want it to fail if it already exists. The exclusive bit. So this will open it for read and write and create it. However, if it already exists, this bit here has been flipped, then this will return -1. Okay. So I think this is on the right track. However, I would say what you want to do is you want to get everything locked up prior to dealing with the shared memory. So you have the exact same conceptual idea here, except what you want to do it with is you want to do it with semaphores. So the very first thing you do is you try and create the semaphore with the exclusionary bit and let it fail if the semaphore already exists. Okay? So if this fails, then you're not the first player. If it succeeds, what is the very next thing you should do? You should, so let me talk. Here's the number that's provided. And then what I can do is I can, the two calls that are of interest are on lines 28 and 39. SemWait and semPost. So semWait grabs and semPost releases, and what it's grabbing and releases is a value here. So if this is 10, then if I do a semWait, it goes down to 9. If I do another one, it goes down to 8, so on and so forth. We want to use this similar to how you'd use a mutex with threads, and I just want to toggle on or off. Okay, so I create it with 1, and assuming that that succeeds, then the very next thing I do is I grab it with a semWait. Yeah, and so now the 1 goes down to 0. The significance of it is if someone else tries to grab it with a semWait, it's already 0, and their process will literally block at this line right here. And it will not continue until the original process does a semPost, putting that 1 back, and then this other process grabs it.
We'll wait on the semaphore, right? Wait on the semaphore. If it's already taken by someone.
Yes, this is a blocking call, meaning let's actually look at it. I mean, enough of me talking about it. Let me scan this code and make sure. I'm going to get rid of this. I'm not concerned about player 1 or player 2 for this simple example that's here. So let me try. Well, I can do it. So let me see. I want to do that. If that failed, then I'm going to say first player, subsequent player.
Do a fork, maybe.
No, I'm not. In this case, I'm not doing any forks. They're like on different terminals on the same computer. Okay, I'm going to open it, try and create it exclusively. If it already exists, it's going to fail out. It'll come down here and it'll just open it. All right? And then again, this stuff was the permissions that it's opened with. So after I open it, and now I should be doing, there should be more error checking here. I'm dispensing with the error checking for just cruising through this more quickly. This one you don't need to do. I just wanted to exercise the use of the various functions that come with this semaphore. And what you can do is provide it the address of an integer, and I provide it this pointer of the semaphore I've opened, and what it'll do is it'll look at it and it'll tell me what value it currently holds. It should hold 1 because no one's tried to grab it. Then I print a little and I print it out here, and then I said, okay, I'm going to grab it. And I should error check. I do a semWait to grab it. The first process to do this should have no problem. It created the semaphore. Now it grabs it. It says it just grabbed it. And then I get the value, and I show that it's now down to 0. Then I put a little pause here. That makes it easy for the demonstration. After the pause, I go ahead and release the semaphore. Okay. And then I close it. And then I should unlink it at some point, but I won't unlink it. So I say G++, standard equals C++. You could do 11. I wanted 14. What did I need 14? Just over the weekend I needed something from the 14 standard and I don't remember what it was. All right, so I've got, what kind of errors are these? So I'm likely forgetting to add a library. And man sem open and pthread. Okay. Yes.
How are we going to get open multiple processes? I don't see any in the source code, no any facilities for doing that.
No facilities for what?
Like forking multiple, if you want to have multiple processes. That
All right, so the forking is not going to happen in this project. It'll definitely be happening in the following projects. But this one, so why am I not concerned about forking? Because I have two separate terminals. So this one, all right, let me run the first one up here. What is this called, a.out? Okay, I had created it with a value of 1. Once I grab it, if I ask it what it is, it's 0. Again, we're not really concerned about getting the value. We just want to use it as a locking mechanism so we can synchronize access to our shared memory. Now I come down here and I run it. So here it hit the sem wait. I guess what I can do here is I can come here.
I didn't know you could do that. Multiple terminals reading the same executable.
All right. So it did the sem open, showed the value. Note down here it was 0 because it's been grabbed by the first process. And then on the bottom pane here, it's hanging on line 31. The minute I hit enter in the upper left-hand pane, then the upper left-hand pane, where's my get? I hit enter here, my upper left-hand pane is going to post or release that semaphore, in which case this sem wait on the bottom process is going to stop blocking on the call and we'll grab the semaphore. So I come here, I hit enter,
and it makes that one.
and then this one goes ahead and continues to its hit enter to continue. Okay, so this is the mechanism we want to do to make sure only one process at a time is accessing the, let me be specific, writing to the shared memory. So if you're going to write to the shared memory, you have to do a sem wait, do any writes you need to do to the memory, then do a sem post. That will guarantee that that process has exclusive access to the shared memory at that time. Yes?
In this case, when we're writing, that's just when they hit a keystroke, right? That's where we're changing.
Right, so the writing will be moving a person, grabbing a gold, quitting the game, starting the game. So when you're adding your player, right, you're going to generate a random number and drop them on there. Once you have the location, do a sem wait, drop it, sem post. Yes?
So when two different terminals have live updates of changes, like you can see the other player moving, they're both at the same time accessing the memory, right?
Yeah, so two things. One, they're only reading, so that's not an issue. At least the one that's sitting there, right? Well, one person is moving, the other one is just reading. Second, for the first project, at the time I was showing you Project 3 where you're seeing live updates. In this version of the project, when one player is moving around, this other screen is not updating. The minute they try to move, then there's a refresh of the screen and that first player will jump to whatever their current position is. So you won't get live updates in the first project. Yes?
So as you see those two processes that originate from the same executable, they're sharing that semaphore, that shared memory. Can they share that if they're different executables? Say if we execute a.out and ls or some other executable?
Yeah. It does. It's a resource that is in principle available to every process on the machine. It's what's referred to, I believe, as a kernel resource, which means it persists until either you remove it or you reboot. When you reboot, all the shared memory and the semaphores and all that go away. Okay. Where is it? So for debugging purposes, in dev SHM, that's not only where you find shared memory entries, you also find semaphore entries there. So when you're debugging and you need to clean these things up, it's easy just to go to this directory and remove everything in there. All right. When you have good, robust code, if there's a problem and an error, the error code. So let's say you've created the semaphore, you've done a sem wait to get it. Now you're playing with the shared memory. You're creating the shared memory, doing ftruncate, dealing with the map, all that stuff. If there's an error in there, then what it should do is it should close and unlink the semaphore. Right? Clean up your mess if something goes wrong. So that's something that you need to consider. Now I have 5 minutes left, and there's one major topic still to talk about. I may be able to get to it. Get through it. I'm not sure. Let's have a go at it. Let's look at our notes. All right. You're not the first player. Open up existing shared memory. That's not a problem because the name is hard-coded. You know what the name of your shared memory segment is, right? Call Mmap. This one's problematic because let's look at Mmap. Mmap. What information do I need to know to call Mmap? The rows and columns. Another process doesn't have that information. In fact, so you know and I know the executable is sitting in this directory and mymap.txt is sitting in there. So that second process could just open up mymap.txt and figure out that calculation, right? No. Assume that this person's running a copy. Assume the executable is in user bin, and when the first player runs it, they run it with mymap in their own directory, and when this person runs it from their home directory, they do not have a copy of the map. Okay? So we need a way of having subsequent processes being able to get that information. And the insight is you make that part of the shared memory. You store the rows and columns in the shared memory. Okay? So now it gets a little bit more interesting in that we are no longer doing mmap to just simply an array of characters. What we want to do is something like this. We want to say struct, what do we want to call this? Game board. Yes, I don't know if I want to put case letters or not. Call it whatever you want. There's another problem that we have, which is
We don't know how big it's going to be when you do that.
well, I'm thinking of the players. So how do you know whether you are let's have a byte in there that represents the players who are currently playing. So if you're the first person to go on the board, you flip the G_PLR 0 bit for this variable right here. And now when you have to figure out which player you're going to be, you just simply go to this character and you find the first bit that's available. Right? Okay. So this gives me, I'm out of time. So this is going to be, what do we put here? Because what you put here ends up being the map. So you've got, if I do this horizontally, I've got the rows, I've got the columns, I've got the players, and then I have the map. So what will happen if I go down to Mmap, I'm going to cast this to a pointer to one of these game board structures. And now we can access, rather than, so you do things like, what do I want to do? Well, I don't have it here. I'd probably give it a different name. I wouldn't call it map port. Maybe I'd call it game board. Game board pointer. The bit board. So you're representing everything as bits. So this is the bit board. Equals that. Then you can do things like bitboard dot player or equals G_PLR0, right? That's how you're accessing elements of this structure. And note it's just going straight into the shared memory. So the two things that we need to figure out for next time is what do we put here for the map itself? And the second thing is then what does startup look like for subsequent players? Okay? So those are things to ponder, and we will pick it up.
Don't you need more space when you call Mmap, more than just rows times columns?
Yes, absolutely. So if I go to Mmap, what does this become?
Rows times columns plus 12.
What if? Oh yeah.
So what we haven't done is there's still a missing piece here for how we actually connect the map as part of the structure, and we'll kick it off with that next time.